Good morning to all. Today we are discussing about classification of analog to digital converters. Okay, analog to digital converters are classified broadly into two groups according to their conversion technique. In this, the first one is the direct type analog to digital converters, and the second one is the integrated type analog to digital converters. Okay, and now we are discussing about direct type analog to digital converters. In this analog to digital converters involves comparing a given analog signal with the internally generated reference voltage. It means that here we are consider the one analog to digital converter circuit. Okay, and here we are collecting the output signal, and here we are applying the input signal. We know that here we are giving the input signal is the analog signal, and here we can correcting the output signal is the digital signal. It means that these analog to digital converter circuit can be converting the given analog signal into digital signal. Okay, but in this process this analog signal internally generating the other analog signal or another reference voltage signal. It will comparing these two signals, it will providing the output. This conversion technique we are called as direct type analog to digital converters. Okay, and in this direct type analog to digital converters we are discussing the following groups. Okay, in this first one is the flash type converter, and second one is the counter type converter, and the third one is the successive approximation type converter. Okay, and the second analog to digital converter category is integrated type analog to digital converter. In this integrated type analog to digital converter, the analog input signal is first converted into a linear function of frequency or time, and this is subsequently converted into a digital code. It means that, for example, here we are considered the one analog to digital converter, and we know that this converter circuit can be converting the given analog signal into digital signal. Okay, for example, we can assume this analog to digital converter is the integrated type of analog to digital converter. At that time, this converter circuit first of all converting this given input signal into a linear function of time or frequency, and later that function can be converted into digital signal. Okay, so this is the integrated type of analog to digital converters. Okay, and again in this integrated type analog to digital converters can be classified into two types. That is, first one is the charge balancing analog to digital converter, and the second one is the dual slope analog to digital converters. Okay, today we are discussing about flash type analog to digital converter or parallel type analog to digital converter. Okay, the circuit diagram of the flash type analog to digital converter I show in figure. Okay, this flash type ADC is the fastest type analog to digital converter, and it is expensive. Okay, and this flash type analog to digital converter circuit consisting the 8 comparators, and these comparators output is connected to input of this 8 line to 3 line priority encoder. Okay, and in this flash type analog to digital converters we are using the this resistive divider network. Okay, this network can be equally dividing the applied reference voltage. Okay, and in this flash type ADC we are giving the two input signals, that is analog input signal and other one is the reference voltage. So these two signals are given to input of this operational amplifier, and we know that this operational amplifier can be acting as a comparator. Okay, so this flash type ADC we are also called as comparator type of analog to digital converters, because this circuit can be constructed by using the comparators. Okay, and now we want to calculating the this node voltage. Okay, you want to calculating this node voltage, you can apply the voltage division rule. According to the voltage division rules, this node voltage equal to the total voltage, that is V reference into this branch resistance. The total branch resistance, how many here? 7 R by this overall resistors in this branch, that is 8 R. Therefore, this node voltage is V reference into 7 by 8. Okay, and similarly we can estimating this node voltage. Again, we want to estimating this node voltage. Again, we are apply the voltage division principle. According to this rule, we are getting the total voltage into this branch resistors whole by this total resistors in this network. That is, we will get the 6 by 8 into V reference. Similarly, this node voltage is 5 by 8 into V reference. This is the 4 by 8 into V reference. This is the 3 by 8 into V reference, and this is the 2 by 8 into V reference, and this is the 1 by 8 into V reference, and this node having the 0 volt because this can connected to the ground. Clear? So here we can observing the one important point is this resistive divider network equally dividing the these reference voltages. Okay, and now we are understanding the working operation of the flash type ADC. Okay, and here we are giving them analog input signal, and this signal is connected to this comparator circuit, and we know that this comparator having the two input terminals, that is inverting terminal and non-inverting terminal, and here the given analog input signal is applied to the non-inverting terminal of this comparator circuit, and inverting terminal having the this reference voltage. For example, here comparing to this reference voltage, the input signal value is high. At that time, this comparator circuit can be providing output is what? V saturation. This V saturation voltage we are assuming as a logic 1. So here this output is connected to the input of this 3-bit parity encoder, and this parity encoder can be encoding this information into the digital form. So in this way we can get the digital output signal. Okay, for example, here we are assuming this reference voltage is 8 volts. Okay, at the time this node voltage equal to how much here? 7 volts, and this node voltage is how much here? 6 volts, and this node voltage is how much here? 5 volts, and this node voltage is how much here? 4 volts. Here we'll get them 3 volts, here we'll get them 2 volts. This node voltage is 1 volt, this is the 0 volts. Okay, and now here we are giving them input signal or analog signal input is for example 2 volts. So this 2 volts signal is given to input of this comparator. For example, we can consider this comparator circuit. Here the non-inverting terminal voltage is 2 volts, and inverting terminal voltage is how much here? 7 volts or not? At that time this comparator can be comparing the reference voltage with this input signal voltage. It will providing output is minus V saturation voltage. So this minus V saturation voltage we are assuming the logic 0. Okay, and coming to this comparator, here the inverting terminal voltage is how much here? 6 volts, and the non-inverting terminal voltage is how much here? 2 volts. So here this comparator circuit can be comparing these two inputs, and it will providing output is minus V saturation, and this value we are assuming logic 0. Okay, in this way coming to this comparator, here the inverting terminal voltage is what? 1 volt, and the non-inverting terminal having the voltage how much here? 2 volts. Here this comparator circuit can be comparing this inverting terminal voltage and non-inverting terminal voltage, and will providing output is positive saturation, and this positive saturation voltage we are assuming as logic 1. Okay, so here finally with respect to the given input signal 2 volts, we will get the outputs of this comparator are 0 0 0 0 0 and 0, and here we will get the 1, and here output is 1. Okay, and these all values are given to input of this 3-bit parity encoder. Okay, and in this 3-bit parity encoder, this output is the highest priority, and this output is the least priority. So here coming to these two comparator outputs, here we have the logic 1, and here we have the output is logic 1, but this priority encoder gives the most priority to this bit. With respect to this bit, it will providing the digital output. Okay, so in this way, with help of this flash type ADC, we will get the digital output signal. Okay, and now we are observing the truth table of this flash type ADC. Okay, this is the truth table of the flash type ADC, and these are the outputs of the comparator, and these outputs are given to input of the priority encoder. This priority encoder can be encoding this information into digital form. Okay, and for example, here coming to the first condition, we will get the comparator outputs are 0002. Here get the 1, and this information we can encode it into 000. Okay, for example, in the flash type ADC, we will get the outputs of the comparator is 000 and 000 and 11, and here the priority encoded with the priority to this comparator output, and with respect to this consideration, this information can be encoded into 001. Okay, and for example, coming to this last condition, if the all comparators can be providing the output is a logic 1. Okay, in this condition, the priority encoder can be give the most priority to this seventh comparator output. With respect to this condition, the priority encoder can be encoding this information into digital form. Okay, so in this way, we will get the these digital bits at the output of the this ADC converter. Okay, and now we are discussing the advantages and disadvantages of the this flash type ADC. And now we are discussing about advantages and disadvantages of the flash type ADC. Okay, coming to the advantages, high speed. It means that here we are considering the flash type ADC, and here we are giving them more than one input signal. So this flash type ADC simultaneously converting this all information bits into digital form. So here this flash type ADC is have the high speed, and the second one is the conversion time is less. It means that within the very short time, this flash type ADC can be converting the given analog signal into digital signal. And the third one is conversion time is limited only by the speed of comparator and the priority encoder. And we know that flash type ADC construction, we are using the comparator and priority encoder. Okay, so here we want to achieve the more speed. So here we need to considering the operating conditions of the this comparator and this priority encoder. For example, these devices is not performing well, then we will not achieve the more speed. Okay, and next we are discussing about disadvantages. Coming to the disadvantage, the first disadvantage is number of comparators required double for each added bit. It means that here we are considered the analog to digital converter with respect to the given input signal. Here we will get generating the digital output. For example, here we want to get the 3 bits of binary output generations. We are using the how many comparators here? 8 comparators. For example, with respect to the given input signal, we want to generating the 4-bit binary information. Definitely, we are using the 16 comparators. So here 1 bit output increases in the construction of the circuit. We are using the 16 comparators. So this is the one of the disadvantage of the flash type ADC. Okay, and the other disadvantage is the larger value of n, the more complex is the priority encoder. Okay, so these are the disadvantages of the flash type ADC. Okay, thank you.